Okay, good. Yes.
Sure. Can I start
Yeah,
now?
yeah, you can continue. Yes, please.
Yes. So as I mentioned, so in today's talk, I'll just briefly cover the Swift instruments and one of the science cases of Swift, and then we will just have a data analysis session where we'll try to analyze data from one of the instruments that is about the Swift telescope. And if you want to uh, learn more about the Swift telescope, then you can go to this website where they have all the sections regarding science as well as the data analysis on the bottom left. So now I'll just go to the introduction about the Neil Gehrels Swift Observatory. So as you see on the left, this is a relatively compact and a small telescope, but has been doing a lot of great science. And it was launched in 20th November 2004, but it has been operating for roughly 18 years now, even though its mission was planned for a little bit shorter time. Swift is a multi-wavelength observatory, and it was built primarily for the gamma ray burst astronomy. The principal investigator of Swift was Neil Gehrels, and it is named after him. Right now, the PI is Brad Senko, but Neil Gehrels was a legendary astronomer for X-ray astronomy and especially in the field of GRB. So it is now named after him. As I mentioned here, that it is a multi-wavelength observatory. This is a very important feature of the Swift telescope that is important for gamma ray astronomy and gamma ray burst astronomy, and I'll come to it later. So the science goals of the Swift observatory were that uh, it was built to determine the origin of the gamma ray bursts. So gamma ray bursts are these intense burst of gamma rays that come from extragalactic space. And before Swift, we did not quite know what actually caused these gamma rays, and so the Swift telescope was built in order to find the origin of this gamma ray burst and also to classify this gamma ray burst into different types and also to search for new types that had not been discovered by then. And also not just to study this gamma rays burst, but also try to use them to study the early universe, because this gamma ray burst usually happen in let's say at very high redshifts, so in very early in the universe, and so they can be used as tools to study the early universe as well as the high energy universe. So after its launch, Swift has been discovering roughly 90 gamma ray bursts per year. So that is quite a lot and allows us to study this fascinating phenomenon in detail. And if you want to learn more about that, you can go on this website. So now I'll just briefly mention about the science instruments that are about the Swift. So as I mentioned that Swift is a multi-wavelength observatory. So it has three instruments that try to see the universe in three different wave bands. So the BAT burst alert telescope sees in the gamma ray band, and X-ray telescope sees in the X-ray band, and U-boat sees in the UV and optical bands. And together they try to study the gamma ray bursts. But the features of these instruments have made them very good for transient astronomy as well, and I'll come to that later. So on the right we see the image of the Swift telescope, and right here we have this burst alert telescope BAT instrument, which is a coded mass instrument. And these two pipes here, pipes like stuff here, these are the U-boat telescope and the X-ray telescope. So one key thing here about these instruments is that BAT is a wide field gamma ray transient detector, whereas the XRT and U-boat are narrow field telescopes for studying the afterglows of these events. So by wide field, I mean that it observes the sky in a larger area and tries to then find the gamma ray transients, so these events which release gamma rays suddenly. So and XRT and U-boat are narrow field, so they can study in X-ray and UV wavelengths, but in a smaller area. So and these were especially designed when Swift was being to study gamma ray burst, and I'll try to just mention the science case of the gamma ray burst that I studied with Swift. So if we just try to read this phrase here, Swift GRV response, it could mean that we are studying the GRV with Swift, but Swift also means that it is fast, and Swift does need to be fast in order to study these gamma ray bursts because they happen suddenly, and the gamma ray burst lasts only a few seconds, and after that the afterglows in the X-ray and the ultraviolet wavelengths fade away quickly. So if we want to study the GRVs, we have to find them quickly and then localize them and study them promptly with other wavelengths. So as mentioned here, the burst alert telescope, which was the coded mass instrument that sees in the gamma ray, finds the gamma ray triggers on the gamma ray burst and calculates the position to roughly 3 arc minutes. So it kind of finds within 10 seconds area on the sky where the gamma ray burst have been observed. Then the spacecraft automatically slows. Slows means it rotates to this position so that these other two instruments can point toward it. And then once the burst has been pointed to, the X-ray telescope sees it in the X-ray wavelength and localizes its position within 3 arc seconds, which is smaller than this area. So as you see, the inset of this goes here, and this is the area that is seen by the XRT instrument. And then the ultraviolet telescope images this field and gives us this UV and optical image, and then returns a finding chart to the ground. Ground means to Earth, so that this finding chart can be used by other telescopes in order to study this GRV afterglows. So I give the example of GRV that was studied by Page et al. In this paper, GRV 080307. So as you see, so there is a at the start of the burst, there is intense gamma rays, and this is within, let's say, 100 seconds, which is less than 2 minutes. So the gamma rays are here. Then after that, the XRT instrument follows the X-ray afterglow of the event in X-ray wavelength, and then also the U-Boat instrument also studies it. And one thing I want you to notice here is that when we go to this time, so this is roughly 1 lakh seconds, and this is roughly 1 day. So within 1 day, the flux has dropped by roughly 6 or 7 orders of magnitude. So these events get faint quite quickly. So the Swift does need to be fast and detect them fast, and then study them with instruments promptly. And with this finding chart, since we know that where the gamma ray burst has happened, the other telescopes on the ground can study this event quickly. Otherwise, this event may not be detectable anymore. So this is the first thing here. And so this is in gamma rays, this is in X-rays, and we also have the optical and UV. So this is multi-wavelength, and this is also rapid response. So this factors made Swift really good for studying gamma ray burst, but these factors also make it good for studying other transient events as well, because it is rapid response and it is multi-wavelength, and also can be used in conjunction with other telescopes that we have in space as well as on Earth. So it is mostly used for gamma rays, but also it can be used for studying, let's say, supernovae or tidal disruption events, or let's say flaring blazars, and we'll try to focus more on the blazar part today. So now I'll move to the description of the XRT instrument. So one important thing here is that this XRT instrument was able to follow this GRV when its flux decreased by roughly 5 orders of magnitude. So this instrument has let's say, a very large range of flux that it can detect, and so it is one of the workhorses of the Swift telescope. As I mentioned, this X-ray telescope studies the GRBs and their afterglows and measures their fluxes, so the counts that are received, spectra, and as well as the light curves. And so it has this Volter 1 telescope, which I think Aditya covered in her lecture. So these uses this nested, let's say, mirrors in order to focus the light, and also these CCD2 CCDD detectors. So it has an effective area of 120 centimeters square at 1.5 keV energy. So one of the reasons that it has this large energy range that it can cover is that it has different modes of operation. So now I'll try to describe these modes. So this time zero is the time when the gamma ray burst was, let's say localized by the BAT instrument, and so this is the time of the trigger. And then once the trigger has happened, the Swift telescope moves to the position of the gamma ray burst. So this is referred as the slew. And once it has let's say pointed to the direction of the gamma ray burst at this point, then the imaging mode starts and just roughly finds the image of the region. The photodiode mode tracks the afterglow. After that, the window timing mode takes over, and then the photon counting mode finally takes over. So as you see, the flux is tracked over many orders of magnitude here. So and among these four modes, the two most important modes that we need to analyze during our analysis is the window timing and photon counting mode. As of now, the photodiode mode is inactive because Swift telescope was struck by a micrometeorite in 2005, and then after that, this PD mode could not work correctly, so it is now inactive. So when we are trying to analyze the data, we'll be focusing on the window timing and photon counting mode. And more information about this X-ray telescope can be found in this instrument paper of Burroughs 2005, as well as the Swift technical handbook that you can find on this same website. So now before I go to the data analysis, I pause for any questions if there are any. Please let me know if there are any questions.
There is one question already in the chat box.
Okay, I'll see that. So what is the difference between the imaging mode and photon counting mode? So I'll try to just describe this. So just let me 1 second. Can you see this? Let me share. Yes, can you see this now?
Yes, yes, yes.
Ah,
We can
yes.
see that.
So this is just an extra slide that I had. So we are trying to find the difference between the imaging mode and the photon counting mode. So the similarities are that both the imaging mode and the photon counting mode see the, let's say, the object in 2D. So they give this spatial information, but the difference between the imaging mode and the photon counting mode is that the imaging mode does not get spectroscopy, so does not get the spectral information, whereas the photon counting mode stores this spectral information, so it is available. So this imaging mode is mostly for, let's say, localizing the GRB or other transient event after it has been provided by the BAT, whereas the photon counting is more for, let's say, the science analysis. So when we are doing the science analysis, we focus on the photon counting mode, and the imaging mode is just, let's say, for good pictures. So I hope that helps. I'll restart again. Does that answer the question?
Yes, yes. Thank you.
So now, can anyone hear me?
I can hear you.
Okay. So now I'll just move on to the data analysis part. And everyone should have received an email today where we asked you to download the Swift data analysis folder. So it has both the spectral part as well as the light curve part that I'm trying to cover right now. So please download that. And So now I'll just go to the data analysis part. So we'll try to cover the data download, and then we'll try to, let's say, create cleaned event files using the Exati pipeline. And then we'll try to generate the products using Exati products. And finally, we'll create light curves. The spectral part will be covered by the next speaker. So the things that we asked you to do before the workshop were just install Hiasoft, which is necessary for this Swift analysis. Similarly, the calibration database files should be set up for the Swift instrument ahead of this workshop, and also we need to download the data. And once you have installed the Hiasoft, then also let's say install the calibration files for the exact instrument of the Swift telescope, then you can test if it is set up and running successfully by using this command. And finally, these were the download links using the duplicate command that were used to retrieve the files. And but one question that you could ask, unless you did it yourself from the Swift master catalog, how did I get this, let's say, these links? So before that, I'll just mention about the object that we are trying to analyze the data for today. So we'll be analyzing the data of the Blazar MRK 501, which was studied by Benjamin Markarian in 1974, and it is at the redshift of 0.0034. And here we see the optical image of this MRK 501 from the Sloan Digital Sky Survey. And let's now see how it looks in the X-ray wavelength from Swift XRT instrument. So this is the MRK 501 in X-ray wavelength. And once we analyze this data for this MRK 501, we can create, let's say, light curves like this one. So this is the full light curve of this object from 2005 to 2021. So roughly 17 years of data. And we see that this object does flare up a bit, then goes down, then goes high again. So this is the low state, and this is the high state, and this is the low state again. So there is some kind of periodicity, but I'm not going to comment on what exactly the periodicity. But we can find more information about these blazars that have been observed by Swift and also other blazars in this Swift PSU monitoring website. So our aim for today is that we will not try to create the whole light curve, but this light curve was made from many observations that were done at different epochs, and only trying to just create a small light curve for one particular observation. Then once you have that skills, then you can let's say analyze it iteratively and create the full light curve yourself. So as I mentioned, the essential bit here is to find the data first, and that we can do it on the Swift master catalog. I'll just mention it a bit here, and then I'll try to show it by going on the website itself. So we go to the Swift master catalog, and we, let's say, pick the observation IDs and separated by this semicolon, and we also select the object name, and we then filter the observations as per our necessity, and then we create the download script, which is the script that I had sent in the description. So here we pick the object name, and then we filter the observations. So we select them, and we can also sort them by the exact exposure time, and then we create the download script, and this is the script that you saw earlier in that snapshot. Finally, now I'll just go to the website so that you can, let's say, later find and download this data as well as per your requirement. Can you see the website?
Yes, Ayush, yes. It is
Okay,
visible
so
here. Yeah.
okay. Okay, so this is the Swift master catalog. So and here we can find the data for the Swift telescope. We can find the data for the BAT, the XRT, and UBOT at the same place. So here important things that one could let's say give to this query form is, let's say, the name of the object, the observation ID, the right ascension and declination of the object, the start time of the observation, and this exact exposure is the time that the object was observed for. And similarly, we have the U-boat exposure and the BAT exposure as well. And so these are the main, let's say, things. There are other things, and you can study up, you can find about them on the Swift Master Catalog description itself. So now I'll just, let's say, pick these two observations. This is a WT observation and this is the PC observation. Uh, so window timing and photon counting, and then you just go down here and set the name of the object marking 501, and then you click start search. Then once you have done that, you get this page where you see this DSS image as well as the information regarding the observations. So, and then what you could do is, right now, the observations that I have selected, they all of them have, let's say, XRT exposure above 1,000 seconds. So you can, let's say, set the limit of this XRT exposure as well in the earlier form. Then you select, let's say, these observations, and then you can also select which data you want to actually download. So right now I just said that I want to download full of all of the Swift observation, but you could just say that you want to just find the auxil, log, and XRT data. So if you want to analyze the XRT data, then you need both the auxil as well as the log, because these are the auxiliary files that are very important for the analysis, and these are the log files which can be used by the XRT pipeline as well. So once you have done this, then you just create the download script. Then this download script would be ready, and you can then copy this and just use it for the further analysis, for downloading the data for further analysis. So this is the Swift Master Catalog thing. So do you have any questions just for the data download part? If please leave in the chat, I'll see that. If not, then I'll move on. So hopefully you have downloaded the data for these observations ahead of the workshop using the wget command. Once you have downloaded the data will look like this. So you'll have this, let's say I downloaded this data to the workshop folder, and we have this observation folder. It will have these 5 subfolders, and so the main important folders are the auxil folder, the log folder, and the XRT folder. And for future analysis, I want you to remember the locations of these important files. So in the auxil folder, we'll have the primary and secondary attitude feed files, and also this orbit ephemeris file, whereas the XRT folder will have the XRT data, which includes the event files, which are used to extract the light curves as well as the spectra, whereas the housekeeping files are important files that are used for the analysis. So once you have downloaded this, you should be able to at least see the auxil, log, and XRT. So if in your analysis you do not have this auxil folder, then the analysis may not happen. So you need to remember to download at least this auxil, log, and XRT folders for the Swift XRT instrument. If you want to do, let's say, U-word analysis, then you need this folder, or if you need the BAT analysis, then you also need this folder. So then once you have done this, you can then create cleaned event files using the XRT pipeline command. So the data that you have downloaded to these folders is level one event files. And when you, let's say, clean them, then they become the level two event files, which you can use for analysis. And and for this XRT pipeline instrument for command, the let's say the command is as follows. You have this XRT pipeline command, then you need to supply the in directory, so the input directory where the files are located, the stem inputs, which is the file name that is used, and the output directory where the data will be returned to, and the source write extension and the source declination. So these can be obtained from the NAID catalog, which is the NASA extragalactic database, and gives the information for this source array and source tape. Finally, you clean up no means you do not throw away important extra temporary files that are formed during the analysis, whereas Clover removes any files that may have already formed. And this create expo map creates the exposure map. So this is about the exotic pipeline. Now let's try to see this in action. Uh, so so I'll do is I've already created this output folder. Now I'm going to delete it. So now let's start a new terminal. I've already initialized the AI init, the Yasoft, and then I navigate to the folder. So now let's see the contents. Please confirm if you can see the terminal because
We can't see your terminal.
okay, thank you. So okay, so now, so this is the observation folder for this observation, and so this has the input files. Now we want to, let's say, create an output directory that has these cleaned event files, and we can do that using this command. The
Hello, Ayush.
yes,
Your I think command tab is not shown here.
you can see the terminal, right?
No, no, no.
Okay, yes, here screen. Can you see that? Can you see this now?
Yes, now it's visible.
Okay, thank you. So I take this exact. You can find this, let's say, this record of these commands in the commands.sh file that is present in the drive folder that I mentioned earlier. You just download that, and you can find this commands.sh with the steps. So now I'll take this exotic pipeline command, and now I go to this folder where I have the observation input directory. Then when I do this, so I supply the input directory, which is this same folder, the stem inputs, which are used for naming the output files, the output directory, which stores the output files, the source write extension and source declination. Then we tell the XRT pipeline command to create the exposure map as well and remove any files that may have already been there, and also just not to throw away any important but temporary files that are found by this XRT pipeline. So now I'll just run this, and it will, if I have supplied the correct values for these inputs, then it will uh, run correctly. Otherwise, it will let me know. So it will take some time because this is a very intensive process where the anxiety pipeline runs various tasks on the input data and creates these event files which are cleaned and can be used for future analysis. So just let's wait for a minute. In the meantime, you can also, if you have downloaded the data, you can also run it on your own PCs. So this is good. As you can see, XRT pipeline ran without any errors, and now we have these cleaned event files and also other files. Now let's try to see which files are there. So now I'll just go back to the, so now I can just go to the output folder. So this is the output folder that has been formed, and it will have, let's say, these files that we have created. So let me clean. Yes. So can you see these files? So these files. So the cleaned event file is this file with the extension cl.evt and this PO, which refers to pointing. So this is the data which is taken during the pointing mode. So the data, if it is taken during the slewing mode, when the telescope is rotating towards the source, this data is not used. But when it has pointed to the source, then it takes the data, and this is what is used for analysis. So this, you need to use this o underscore cl dot evt file. So this is the event file, and just above it, you can see this xsd pc.sk file, which is the housekeeping file, and it is also important for the analysis. And finally, you also see this exposure image. So I did not mention earlier about the exposure image. So this exposure image file is also very important for analysis, because it finds if there are any pixels that have not that are not correctly storing the values. So this those pixels need to be removed for the analysis, and this exposure map stores the exposure of the instrument to that source at that observation. So these exposure maps are unique for every observation, and they need to be taken care of. Finally, there is also this po.rec, let's say, region file. So earlier we set this cleanup is equal to no. If we had set it to yes, then this .rec file would have been deleted. So this file can be very important because it is centered at the source observation. So now I'll just go back to my slides for a minute. Can you see the slides? The next slide.
No.
Okay. Yeah, now?
Mhm. Yes. Now I can see the slide.
Okay, so once you have run the XRT pipeline command, and then you have this directory with the output, which is roughly the same as I shown earlier. So we have this event file with the postcl.evt extension, the escape file, the housekeeping file, and the exposure image. So these are the important files that are used for the analysis. So now once we have done this, one thing that I should mention is that XRT pipeline does have more options. Can you see the terminal again?
No, no. Now your presentation is seen.
Okay, sorry. I'll have to ask you many times today because I need to switch it. So sorry for that. Can you see this?
Yes, yes.
Yes. So if you want, let's say I give you this, let's say, options like create expo map or clover or cleanup. So these values, these input parameters, if you want to know which input parameters are available for any particular command in the Yasoft package, then you just need to write help, then the command name, then you, let's say, get this description, and you can find, let's say, um, the usage method right at the top. So this is the XRT pipeline, the input directory, output directory, stem inputs, source array, source state, and so on. These are the optional parameters. So they have been they are inside the square brackets. Then you can navigate down to this navigate down the description, and you can find, let's say, the different parameters, and based on this you can, let's say, supply other things, and so if you want to see that, you can go here, and so this is as of now. Now I'll go back to the slide again. So I hope you can see it now. So now, once you have, let's say, uh, run the Exati pipeline command and got the cleaned event files, then you have to then apply a small barycentric, barycentric correction to the event files. So as you know that the Swift telescope is moving around the Earth, and the Earth is moving around the Sun. And sorry for the typo, I have, I think, written here Chandra, but let's take it Swift now. This is true for every telescope. So we have this Swift moving around the uh, Earth, and Earth moving around the Sun. And as we know, there is general relativity, and this causes difference in time arrivals for the X-ray photons, and that can come in the way of precise timing analysis. So this barycentric correction can help correct for the Shapiro time delay, where due to the gravitational potential, the X-ray photons take a bit longer, and this can get in the way of analysis, because when we are trying to do the timing analysis, we want the detector as well as the object to be in an inertial frame. So when we do the parasitic correction, then we move to an inertial frame. So for doing that, we just have to run this barycor command, and we supply the event file. The output file name is basically, we add this underscore bary so that we can recognize it. And the orbit ephemeris file is keeps the, let's say, the path of the satellite in space, and so that it can be used by this barycor task to find out the time delays that need to be accounted for. And at this moment, you also need to correct for the housekeeping and attitude files, because these are also, this can also be affected. So now let's just do the Bary correction. I'll go back to the terminal again, clean the terminal. Once I have done that, so as of now, I do not have the barycentric corrected files. What I can do that is, so as I mentioned earlier, the attitude files and the orbit ephemeris file are inside the observation folder. So in this auxil directory, so this pat file is the attitude file, and the SEO.fits is the orbit ephemeris file. So what you want to do here is, this is not necessary, but in order to just make the lives easier, just copy these files to the output observation folder like this. So just run this, and let's run the other one as well. So now let's go to the output folder. Now hopefully we have those PAT and SEO files as well. We just copied them from the auxil folder to this output folder, because then the work will be a little bit easier. So now, so we have this PAT file, the SEO file, and also our cleaned event file. Now let's apply the Bary core task to these files. So then what we can do is, let's first just barycentric correct the event file. So for this, before I run this, I'll just mention the options. So this is the input file which I have supplied here. The output file just has this underscore Bary so that we can distinguish it. Then this orbit files is the SEO.fit files that I mentioned earlier. Then you just run this command. The barycentric correction has been done correctly. Now you just correct the attitude files as well. So you run that. and that is also corrected. So now let's see the files. So as I see, as we see here, the event file has been barycentric corrected, and this is the file that we will be using in the future. Similarly, the attitude file has been barycentric corrected as well, and this is what we will use. Finally, this is here, we have this housekeeping file as well, which we also want to correct. And for doing that, what we do, we also run the same task again, just changing the input file name and output file name. For all the files, the orbit ephemeris file, SAO.fit files is the same. So I have now, let's say, done the barycentric correction. We have this barycentric corrected file, we have this barycentric corrected event file, and we have this barycentric corrected housekeeping file. So we have taken care of this time delay. Now what we can do is, so now let's go to the main part. I'll go to the slide again. So we have done this barycentric correction. If you want more information regarding this or separate time delay, just see this paper and also see about these links. So now so now we have done the barycentric correction. We have the cleaned level 2 event file. Now we can start examining the data. So let's try to just examine the data as of now. So for doing that, we use this xselect command, and we just so this is included in the YASOF package. And once you just initialize it, you can first of all set your session name, and then you can read the event file. Just remember to give the right file. So we have the cleaned event file. Then we give the input directory. We say reset the mission, and then we can extract all products, or we can just extract an image. And in doing that, we'll also get this information regarding the fits file. And this is an important part here. We check the counts per second for this image. And this is important because we need to check for pileup. It has been mentioned in the other presentations as well, but I'll cover it again. So for XRT instrument, the pileup may happen for the WT mode if the counts are above 100 counts per second, whereas for PC mode, it can happen if the counts are above 0.6 counts per second. So this data was for the window timing mode. And as you see, there is perhaps no pileup here. And one thing before I move on, in this event file name, you can find out which mode it is, which observation it is, by just looking at the file name. So this SW refers to Swift, because this is a Swift observation. SW refers to Swift. Then you have this from 00011184023. So this is the observation ID. Then we have this WT, which is the window timing mode, and this W2 is the window of that mode, and X just refers to the XRT instrument. So, and also this is the pointing mode, as I earlier mentioned. Pointing, the data has been taken during the pointing, so it is PO here. So if this was a PC mode observation, then we'll have, instead of WT, we'll have PC, then we'll have some window like W4, and then we can find out that. So this, as you see, this is a WT observation. The counts are not greater than 100, so we may not need to check for pileup. But anyways, now once we have done, for examining the data, we then open this in DS9, and if you can see, the data for the window timing mode are one-dimensional, so they are taken in a row, and we do not have, let's say, other spectral information, but we have, let's say, a greater time resolution and full energy resolution. So about the events, we can find the energy of that event more nicely, and this has more timing resolution in comparison to the PC mode, where we have this 2D information, as I earlier mentioned in answer to the question. So this has two-dimensional imaging, but its time resolution is is not as good as WT. So this is 1.8 millisecond. So the data is taken every 1.8 millisecond, whereas for this, the data is taken at 2.5 second. But we still have the full energy resolution. This is in contrast to the imaging mode, which was just for, let's say, imaging the source. Once we have opened this these two, so as we see, our WT mode did not have pile up, but our PC mode may have pile up. I have checked and it does have pile up there. Now before I move on, I'll just mention a few important things that we need to take care of when we are analyzing Swift XRD data. This is also true for perhaps any other X-ray instrument as well. So first of all, if you can see there, this is the MRK 501 source, but away from the source we have some counts in the periphery as well. So these photons may not be coming from the source; they may be due to some others, let's say some other things. And so when we are trying to, let's say, find the count rates of this source, we need to subtract the background. Similarly, I mentioned earlier that we need to check for pileup. So in the central region, if there are, let's say, very high count rates, then we may have pileup. So we need to check for pileup every time before we do the analysis. And finally, as I said, this is a CCD detector, and so we need to find these exposure maps which give the response of the CCD pixels to the source. So there may be some pixels that are not taking the data, and that can lead to a loss of flux. So we need to correct for that, and the tool for doing that correction is the exposure map. So when we analyze the data, before we do the other things, we need to background subtract, we need to do the pileup check, and we need to do the exposure map correction. And so now I'll try to just perhaps, first of all, let's just go to the Excel task and try to run that. So I hope you can see the terminal now. Please let me know if you do not see it, otherwise I go on. So I'll just run this select task, but first of all, let's just see the files that we have again. So we have this cleaned event file here, so we'll be using this for the analysis. So we run the select task, supply the name, just random name sum, and then we read the event file. So this is a X-ray of XRT instrument, window timing, pointing, cleaned event file, barycentric corrected. So this is the full file name. Yes, and this input directory is the same because we are already in this this folder where we have this event file. So we can just supply /. Then we reset the mission. So now let's do the extract all. So, and we just see the same things as earlier. We have this counts per second information here. And one thing we could do is we just, let's say, extract the image only here. And then we save the image at, let's say, PC1 something or tutorial. Yeah, and then so this has been saved to the tutorial.img file. Then we, let's say, exit, say this is a no. Now let's see if it has been created. So yes, this is the file. So as you so now let's try to open DS9. Can you see? Can you see DS9? So now I just open this tutorial.img file. So we have this small, let's say, one row of data for this WT mode. We can bring it, let's say, forward by maybe changing the scale and also the color. So as you see, we have some data here. So now once I have done this, so this WT mode did not seem to have pile up, but now what we can do is, let's say, open regions. So this is the file that was created by Exati pipeline. So if you set cleanup is equal to no, you have this .rec file, otherwise it will not be there. So I just load it into the current image. So this can be used for future analysis. So we have chosen the source region, and then what we can do is, let's say, create new regions for background. So let's take the background region away from source. We can take, let's say, a circle as well, or we could take many circles and then later average for them, or what we could do is we could take an annuli that is centered at the same position and then use that annuli as a background. So once you have done this, what you can do is you can see the information regarding this. So let's just first see the information about the source region. So in this physical units, so this is roughly 20 pixels wide. The radius is 20 pixels. So while choosing the background, try to, let's say, choose a background that is a little bit more so this is roughly 70. So that we can get more statistics for this background counts, and then we can then subtract. So that we are getting the average background. So let's say we are taken close to the source, then we may have a higher background. In some region, there may not be counts. In some other region, there may be counts. So we want to find the average background. And for that, we can choose let's say, choose a larger circle and then use it to find the background counts, background average counts. So then once we have, let's say, defined these regions, so this region was, so this source region was defined by the Exati pipeline. But what I can do is for the background, what I can do is I can just create this annulus, maybe centered here. Let's centroid it so that it is now centered at the position. Then we just change the inner and outer radius, and then after doing that we can save the regions, and let's give it the name like PO back so that we can save the region. So once I have done that, let's click OK, and I'll stop share again. Can you see the slides now? Yeah, so I'm now on the slide. So as I mentioned, the first step of these corrections have been done. So we have chosen this source regions, and we have also done this selected region for background subtraction. But this was for an observation where we did not have the pile up. So in our case right now, we have this circle at the middle. But when there is pile up, what happens is, so there are very large number of photons coming in. So the more photons we have, the more probability we have for those two or more photons to strike at the same CCD same position on the CCD frame, and these two photons then may have overlapping charge distributions, and because of that, the CCD may register those two photons as just one event. So those two photons will be registered as one event. So what this causes is that instead of two counts, we have just one count, and similarly, instead of two softer, which means low energy X-rays, we have one higher energy X-ray photon. So this leads to spectral distortion. So if we just saw the spectral distribution of these counts, then will not will the we'll have, let's say, a flat kind of spectrum in the distribution, I mean. And also this leads to flux loss as well if the charge distribution has a pattern or grade that is outside the true X-ray element, and this is the values used by XRT. So when there is pile up, in this example, we did not see a central hole, but if there is extreme pileup, then in the center of the image, we'll have this black central region, which needs to be excluded because in this region we have, let's say, we cannot trust uh, the data that has been received. We have, instead of 2 photons, we have 1 photon. Instead of a soft photon, we have a hard photon. So we need to correct for this pile up, and so we do that as seen in the picture by just instead of you choosing a circle, choosing an annulus as I saw earlier, where we just set an inner radius here and then an outer radius, and then we can use this for filtering our analysis later. And so essentially what we are trying to do here, I'll just try to show with a infographic here. So for the XRT instrument, the point spread function is a king function with a Gaussian element. So this is the Gaussian element, and this is the king function element. The value of RC is 5.8, and the value of beta is 1.55. And as I mentioned, we need to check for pile up for discounts. So if there was no pile up and we had just had a point source acting on the detector, then the shape of the image that is produced is the point spread function. So this is the, let's say, the distribution that we should have observed for the PSF. But in case of pile up, we'll have let's say this kind of random piled up PSF here. This central region is the center and the outer region is the wings. And so what we are now trying to do is, so this central region may be the black part in the earlier image. So this black part, as we go away from the center of this source, so we go away from the center of the source, we have this PSF, and we have this central part. We are trying to remove this central part. So let's mask this central part, and then we have just these wings of the PSF on both sides. So then we take these wings, then we ask a question. So we have these wings of a random PSF. We then ask the same question, that what, let's say, PSF function modeled by this, let's say, parameters would have the same wings. So we try to fit this PSF using these wings. Since then we have, let's say, as you see right in the corner here, we have kind of fitted a PSF which has this profile, and also these wings as the same as that of the piled up PSF. Then we remove the mask like a magic trick, and we find this actual PSF. Then we just see where this piled up PSF in orange deviates from the actual PSF, and that point of divergence is the reason for exclusion. So that is, let's say, from the center, this is the radius at which we set the inner radius of that annuli, so that we miss this central region. So this is done inside the X image, which I'll try to show maybe at the end once we have completed the full process. Let's first do for the WT. Later, we'll try to do for the PC, which has been piled up. So this is for the piled up correction. So as I mentioned, we find the PSF that has the same wings as the piled up PSF, and we find the location at which it diverges. And if we do it in X image and other things, we finally find this point of divergence. So this white is the let's say the king PSF, the actual PSF, whereas these cyan lines are the piled up PSF, and the piled up PSF deviates from the actual PSF at roughly 10 arc seconds, which would be roughly 4 pixels, and 4 pixels. And then we can use this 4 pixels as the inner radius of this annuli, and then we can remove that central pile of region with this help of this annuli. So we filtered that region out. So after doing that, we have this, let's say, region files. So this will be saved as a source region file, and we'll also have a background region file which is farther out, maybe as a circle or a background which is an annuli as well, or maybe even a box in case of WT. And then after doing that, we can supply these background regions and source regions to the generating products command, which is the exact products command. So I'll first of all, let's just do for the WT. For this generating products, so this exact products is a command that runs many tasks. So this, rather than one task, it runs many other tasks that perform the corrections as well as calibrations and other things. So if you wanted to do this background subtract, so the inputs are the cleaned event file that we supply here, the source region file, so that we can from that, let's say, image, find the source region, whether it is a piled up region or it is a normal region. We can use this region file to tell the exact product task where we are taking the source from. And if we are taking the background region, we take this bg extract is equal to yes, and we supply the background region file as well, so that we can tell where the background is as well. Then I mentioned the exposure correction, so we supply this exposure file that was created by exact pipeline, and we say correct lc is equal to yes. Then we then we can also choose the energy range. So the exact instrument sees from 0.2 to 10 keV. We can choose any range in between that, and we just multiply by, I think, 100, and we can get the mapping from this is in energy and this is in channels of that detector. So we can multiply by 100 for the required energy range. So 0.3 into 100 is 30, and 10 into 100 is 1000, and in that way we can let's say choose the energy range which we are trying to focus on. Then after doing this, we can just run the exact products command, and we'll have this source light curve which has been exposure corrected, and we'll also have this background light curve that can be used for let's say background subtraction in the next step, but I'll go to that after running the exact products. So we have this, so we can just see by the naming. So this is Swift, observation ID, exact instrument, window timing, window pointing. Then we have this SR, which means source, and we have this corrected. So this is exposure corrected, and this LC just means light curve. And similarly, instead of SR, we have this BKG, which means background. So now let's just first extract the products for this WT observation, which was not pile up. I hope you can see the folder now in the terminal, sorry. So now what we want to do is, so as I said, we have selected this background region. So you can see the contents of this background region as well. Just concatenate it. You can see that it is an annulus, and so we had taken so this is not piled up, so the source region is just a circle with a radius of 20 pixels centered at this location, so it is a circle, whereas the background region is an annulus centered at the same position, but this is the inner radius and this is the outer radius. You can save these written files in different formats. Right now I have saved these in the physical format, so we just have this annulus, then we have the XY position, and then the radii. In the other formats it will be different. So now as I mentioned, we do have the background region file, we have the source region file, we have the event file, we have the exposure file. So I think we are ready to run the exact products command. So now I'll just first, from the file that I showed earlier, I take that command. So now before I run this, I'll just mention about the options again. So this is the input file. the cleaned event file. The region file is the source region. We are extracting the background counts. So this is the background region file. Then we have this output directory where we are going to store the products. Then we have this, let's say, STEM output refers to options for the file names. Then we have this exposure image. Then we correct the light curve using that exposure image. We have the attitude file, and we have the housekeeping file as well. We select the energy range and we remove any files that may have already been there. And this is an extra option for correct LC. Just set it to WT and frame is equal to 0. Then I'll just run this. So yes, we have successfully created the light curve, the spectrum, and the image. And so as you see, there are many options. If you forget them, then you can see that commands.sh, or again you can just do f help exotic products, and we will have this description again, and all the options will be described here. So all things I mentioned are here, and even more of them, like bin size, which I did not do here. So bin size is roughly time binning. So we take that light curve and we let's say bin it in bins, time bins. So now so once I have run this exotic products, we have this product folder that has been highlighted in green. So now let's see what is in there. So as I mentioned earlier, we have this background light curve. We have this source corrected light curve. And in addition, I will not use them, but there are these spectral files for the source, and I think for also the background, and also this ancillary response file. We can create the RMF as well, but I have not covered it here. So this is it. So I have done the exotic products as well. So I go back. So now we have let's go to the product folder first. Let's do that. Okay, we have this background region, we have this source light curve as well. So now we can do the background correction. So so I mentioned that we needed to do 3 corrections. One was pile up, if there was any. For this observation, we did not have pile up. So we also needed to do exposure correction, which has been done by exotic products. So that has been done as well. The last correction that we need to do is background subtraction, and the exotic products has given us this background light curve and this source light curve. Now we can subtract them in order to find, let's say, this background subtracted corrected light curve. Then we'll just supply some underscore something extension that reflects that fact. It is our choice. So now I'll just go back to the slides again, just to mention about the next step. Just give me some minute. Okay. Okay, so we have generated the exotic products. So now we do this background subtraction, and for doing that we do this LC math, so light curve math basically. So we for doing this we need to supply the input file, which is the source corrected light curve, the uh, background light curve, and the output, which is we now supply this C sub, so corrected subtracted light curve. So that just have this output name. And so as you see that it mentions that these are fits file, and so this is flexible transport system, I think, flexible interchange transfer system for astrophysical data. So so it has some particular way of storing the data. So all these LC files are fits files. Then we need to supply the scaling factor for both the source and the background. And then it has this extra prompt where it asks if we want to add or subtract the light curve. So we want to subtract, so we just say no, and then the light curve will be corrected. And as I mentioned here, this factor is the ratio of areas of the source and background region. So the earlier file that I have shown you, So the source is a, let's say, a circle. The outer part background is a annulus. We find the let's say the ratio between the source region and background region. We can just use simple geometry to find the area and then take the ratio. And then let's now do the background subtraction. I'll go back to the terminal. Okay. So before doing that, what I'll just say is, okay. Okay. So as you see that this is a circle, and so source circle, this is the background NLI, and if you take the ratio between them, the factor comes out to be 0.1. So this is the value that we saw earlier in that let's say slide, and that is the value that we'll be using. So now I take that lcmath command, paste it here. So and before I run this, let's just clean it so that it is at the top and you can see that more clearly. So as you see that this is the input file, and we also supplied the background light curve, the source light curve. Then we supplied the name of the output, corrected and subtracted light curve. Then this is the multi, refers to just the source factor, and this is the background factor, the 0.1 which I mentioned, and we are subtracting instead of adding. So we just do this. Then so this has now corrected the light. It has now background subtracted the light curve. Then we can just see that again. So this is the corrected and subtracted light curve. Now what I'm going to do is, so let's just first see this file. So what does it contain? So what does the file contain? So just let me first start FV, which is the file viewer. Then I'll try to share the whole screen so that it opens multiple windows, so it can be difficult to show. I hope you can see these two windows. Please confirm if not at any point. So we had this corrected and subtracted light curve. We open it. So as I mentioned earlier, this is a fits file. So this has different index headers. So this is the primary header, and this is rate and GTI, good time interval, and region. And so then we go to this rate, and what do we have? We just find the table. So I hope you can see the table. So this table has a time, rate, and error. So then we can try to plot this. So I'll just do this plot. On the x-axis we want time, on the y-axis we want rate. The error goes in y error, and then we just plot it. So we see this jumble, but the reason is that this observation is WT, and it has this millisecond resolution, time resolution, because and because of that we have many observations in this time frame. So now what we do with the next step is that we'll try to bin this light curve in, let's say, a larger time interval, like in maybe 5 minutes. So that for that, what we do is we just first show the commands. We do the L curve task. So I'll try to share the terminal. So as you see, the number of series is this. So the number of light curves. So this is the input file, the corrected and subtracted light curve. And then this 300 is in seconds, and it refers to the time binning that you are trying to do. So you are trying to bin it in 5 minute beans, and then we just apply the finished light curve extension so that we can distinguish it. This is the final output file, and we are not trying to plot it as of now, though we could do it. So let's try to plot it. XW. So I'll just share that plot now. Can you see this light curve? Please confirm. This we have time, we have counts per second in a PG plot window. Dinesh type?
Yes, I
Okay.
can see a plot.
Yes, thank you. So it mentions that we have taken this 5-minute bin. We can take other values, but it has to be accurate as per our analysis. Then we have this WT observation that start at this time and mission time, I think, and then it is offset related to that. So it starts at this and takes up to plus 3000 to plus 3800 seconds, and we have this is the counts, and so these bars are the errors in x in time, and these are the errors in rate. So then we have now let's say plotted the light curve. Control C to stop that PG plot window. So now PG plot is good, but as of now we try to do things using Python. So for doing that, we'll try to just extract this finished light curve onto some other format. Let me find that finished light curve again. Yes. Okay. Just let me a minute. Okay, I found it. I hope you can see this again. So we already plot already this. So now what we can do is just export this using this FP thing. So we have this time, we have the rate, we have the error, we have the fractional exposure, and then what we can do is we export as txt. We set the name as this, and so we have this txt file. We save it, we set the delimiter to comma. So if you want CSP or little bit easier, we can just set it to comma, then we save it, we close this, then we can plot this, let's say file, this txt file that we have extracted using any our favorite plotter. So I have also given you a Python notebook that you can load this data into and then try to plot it in, and basically you will have a plot that just looks like the same as earlier, just a little bit more beautiful. And so this is the L curve, meaning the light curve, and then we have this once we plot it, and then I have also just given you some code so that you can shift this time to MZD, modified Julian date, so that then you can plot this with other observations, and then at the end what you can do is you can just get a plot like this. But you, in order to do this plot, you do this full light curve, you will have to analyze probably 3000 or not 3000, 300 observations in average for each source, but it depends on the source. So for MRK501, it is roughly 300 observation IDs. So, and So all the information that I gave you, it is explained in more detail in these links. You can always go on the website and there will be better explanation. So I'll just stop for questions. I'll just see the chat. Then we can try that piled up also. So as Dinesh Thai mentions there, choosing the region type depends on how you want to analyze your source. Like as shown, like as it was shown for pictoray, if there is a Z, then we can choose that Chandra type of region. So this is actually true, and thanks for answering that. So there is no speciality, it's just our choice. So is there any other question, Dinesh Thai? Please let me know.
I have one question. So what if we have from our source, there is also a nearby source, and which is uh, similarly brighter as the source we want to extract the spectrum?
Right. So I think please correct me if this would be wrong, but in my guess, what would be the thing is that we have this, let's say, two sources, and they are quite close. So it would be kind of like the same as the jet as we saw yesterday. So we can choose a different kind of reasons so that we just uh, choose the source that we are interested in, and we let's say do not take the source that we are not interested in. But if someone knows more, please answer. Does that help?
Yeah, thank you.
Thank you for the question.
Hi. I have a question.
Yes, please.
I want to know that you have King's function
Sorry, could you put it in the chat? The voice is breaking.
Your voice is breaking, Susmita. So can you please type your question into the chat box?
It on top of
Yeah, please, Susmita, type your question in the chat box. Your voice is not audible here.
Oh, so the question is, what is our goal for fitting the King's function, right? Are we trying to make counts? So yes, less than or so we are not in my knowledge, we are not trying to lessen the counts, but what we are doing is we are trying to find by fitting the King's function, because that King's function with that Gaussian element is the let's say the response of that pixel to that X-ray photon. In the case of pileup, the X-ray photon will those X-ray photons will cause that response to be different from the normal case. So we are trying to, by fitting the King's function, we are trying to find the region up to which we are trying to, let's say, exclude that piled up region. So we are not trying to change the determine the counts, but we are trying to, let's say, find the spatial region in which we are going to find the counts. In my knowledge is that, but please correct me if someone knows more.
Right. Actually, this King's function, you can start with what is PSF. Yeah, the PSF is that if there is a point source, how it would appear in your instrument. Okay, this is basically related to your instrument response function and things like that. So as they think that the function can be better fit with King's, this is about their instruments and their response functions. So if you particularly ask why King's function, that's why King's function. Um, I think that helps, right?
So I have a question.
Yes, please.
So in case of window timing mode, suppose we have to take a background selection as a circle instead of annulus. So it should be along the image only, no? Like one dimensional image we have. So away from the source center, that circle can be chosen. It should be along the one dimensional image.
Yes, so I'll just try to go back to the DS9 again. For that, just give me a minute. Okay, I'm sharing the screen again. So this is DS9 here. So do you see that? Just confirm. Then I'll try to just try
Yes,
to answer
yes.
the question. So as you mentioned, so please can you repeat again? Sorry.
So like as you explained, annulus region we can for the background. So if we want to take a circular region as a background,
Uh,
so our
yes, yes. So I think I got you. So as of
that
now, what?
circular region image, right?
Okay, I'll just go on. So you can change the regions, the shape of these regions that you define in DS9 by going to this uh, menu box, and here is this annulus and also panda and other things. But what you can also do is this box annulus. So for doing that, what you could do is let's say you take this source and try to analyze. As of now, just ignore it. For let's say this. So I said for the source you could do this, and I think your question was that we could take the background region maybe around here. So I have not quite seen it, but I think it can be done. Uh, One thing that I have seen is on the exotic pages is that they instead of doing this, what they do is so we have this WT1 row observation. So then they try to let's say do this source region like here, and then they take a bigger and then what they do is so then they take annulus and then uh, what they do is let me delete this first. Yeah, so then what they do is they go towards the edge of this WT observation and try to take the background from here. And also they also do this box type things which I could not replicate here, sorry. So does that answer the question?
I think he's right. I mean, in case of window timing, it has to be a box type. Dr. Adhikari can further comment on this. Rather than circle, because it's a 1D, so you have to have a box, and the background should be of the similar shape.
So I have another question.
Yes, I agree with what Professor Bhatt said here.
Thank you for that pointing that out, Kiran.
Yes, so I have another question. Can you show the image again?
Sure.
The same image, the DS9.
You can zoom a bit more, Ayush.
Yeah. So can I ask?
Yes, please.
Yeah. So, sir, here we can see there is a bad pixel here around the center of image. Uh, what should be the criteria? Because if the source center is so close to the bad pixel, or it is exactly lying over the bad pixel, so that PSF fitting may be uncertain or may go wrong. So, what should be the criteria in deciding whether this particular source should be taken or not? Like how much, how far it should be from the bad pixel, the source center?
Thank you for the question. I'm not quite sure, but I think that if we have that pixels that is very near to the source, then as you said, it can affect the PSF fitting. I did not fit the PSF for this one right now, but yes, it can affect, and I think it should be a little bit farther. It would be easier to point out. I think maybe in the PC mode image, because we have that 2D image and we can see where this the pixel lies in bad pixel lies in relation to the source. But I think in that case also it needs to be, I think, probably, I can't give you a number, but I think it needs to be quite far. But can Gopal sir comment on this?
You have to look at the PSF fitting. I mean, that will only tell us. I mean, just by looking we have to be able to plot and then see where it is. That's the only way. Just by looking the image, I think we will not be able to tell particularly this number should be. We have to do the PSF fittings and pile of correction and those kind of things.
Okay, okay. Thank you.
So any more questions? I think I see still the hand raised by Susmita Agrawal.
Yes.
Can you please type your,
Sir,
because your voice is not.
is my voice now audible?
Sorry, but we could not. Yeah, we cannot hear.
Hello, am I
I
audible
can you
now?
hear what Susmita is saying?
Am I audible, sir? Am I audible now?
No, your voice is not clear. I think there's some disturbance, so it's breaking in between. Ayush,
Yes, sir.
can you read from the chat box? I think there are some. Yeah, Susmita is writing something there.
Yes, I think she's trying to clarify something.
I can read your question actually. I analyzed a source and when I fit King's function to choose the inner radius according to the divisions, I still have count less than 0.5 count per second. What should be done if the PSF is not sufficient to? But it will depend upon what kind of source you are analyzing. For example, are you analyzing a very bright source? Uh, this could be the case. Okay, Asian. Could you name? I mean, I know some of the Asians if this is bright or not. Okay, Blazar. High state, low state. I know some of the Blazars. Okay, BLOC. BLOC is not that bright. I know that. BLOC is like moderate. The brightest are the MRK 421 and then 51. BLOC must be moderately, must have moderate flux. Uh, just from these, it's hard to say from these descriptions. Uh, I mean, I think we should look at it in detail. Just by saying that you did that, and it will depend upon particular observations. And more importantly, did you did you check in the wherever you downloaded the data that it has some issues or not? There are issue tag 1 or 0. Um, did you make sure that it didn't have any issues, some uh, data related issues with this? They will mention that in zero, by mentioning 0 or 1. Uh, yeah, we can take a look if you could send some further details. But just by saying it will be, yeah, you should check one of the things. Wash out of issues, yes, yes. Just go to wherever you download this data, it will tell whether it has some issues or not. The issue 1 meaning there's some issues, and there will be a description of what went wrong or something like SSA or the solar flare, things like that. Probably in Slion mode or something wrong with the instruments. It must have taken in not perfect timing, GDI timing. Uh, that could be one of the issues. But if you could send us the details, maybe we can further comment on this. There's another question by Suhail. You want to take it, Ayush?
I'm not quite sure about that question again.
Can multiple PSF done on the same reason? That's the question of Sohail.
So multiple PSF fitting, is that the question?
Yes, yes. So he's asking if you can do a multiple PSF test on the same reason.
So if the question is that can we fit, let's say, different types of PSF on the same region, then I think there is option for that. Uh, so so this is done inside the XMS package, and there, uh, once we get the PSF core out, then we can, uh, let's say, model it using the King's function, but also there are other functions that we can fit. So I think it can be done on the same region, uh, one at a time, but I don't know if it can be done multiple at the same time.
Yeah, many of these things are also very much clearly given in the manual, right, of new star data reduction process. So you can have a careful look there, and I think most of your queries are already addressed there in the manual. Because sometimes the problems or the queries come when you start analyzing data, and then yeah, you have to look for the right place for the right description. Yeah, and I think so now we will go for the a break, a short one, because the time has already passed after the break. So we will meet after 10 minutes. Right, Ayus?
Okay, thank you everyone for listening, and sorry it was a little bit more than the allotted time.
Yeah, it's fine. I mean, so Dinesh will talk right after this. Yeah. So now there is a break for 10 minutes.